I have shown you the um, complexity analysis of insertion sort algorithm. I have shown the step-by-step analysis. For every step we counted the how many times it will run, and then what is the constant cost of running every step, and then we multiplied the running time of individual steps, and then we summed up running times of individual steps to get the complexity of the insertion sort, the running time, time complexity. But I mean, this is good for individual step-by-step analysis, but when there is the input size, the value of n is significantly large, very, very large number, then we do not really care for individual step-by-step counting anymore. I mean, that definitely gives you an idea. Like for insertion sort, we counted them up, summed them up, and find out for worst case it is theta of n squared. Now, what is this worst case? Just one more summary. Worst case is the usual analysis of running time of an algorithm, which gives an upper bound. Okay, is the maximum time on any input of size n. Okay, so these are the most important keywords here. This is maximum time. Okay, otherwise this is the analysis. The time factor will be is a relation. But here, because we say that it's a maximum one single value, so the relation is being transformed into a function. So this is the maximum time on any input. Okay, this is the important factor. Whatever be the input, the running time will never ever be more than Tn when we are doing the worst case analysis. So it gives an umbrella term. Okay, so this is like it will be less than equal to. It's an upper bound for all kinds of inputs. Okay, so this is the upper bound. Okay, so now you see the average case analysis is that also for insertion service. I told you that if you consider that some of the elements are more than the element currently in consideration, for position shifting, some of the elements are less. In that case, we can assume that okay, maybe some of the half of the elements are less, half of the elements are more. In that way, it's actually easy to do, but we do not really know how many elements are more than the current element in consideration for doing the sorting based swapping analysis, swapping for sorting. So we have to make an assumption that we say that expected time, okay, expected time over all inputs of size n. So expected whenever this is like okay, assume that half of the elements are more, half of the elements are less. This kind of assumption when it comes, it's not just max or mean. It's not a very straightforward thing to do. So then what we do, we say that need an assumption of statistical distribution of inputs. So this we have to know that what is the statistical distribution of input. We have to make an assumption. Like I said, it's a 50% is more, 50% is less. So we have to have a combination of all possible inputs, everything on the world possible for a particular algorithm as inputs. For insertion sort, every possibility under the sun. You can understand that we cannot test with that. So you have to be statistically assumed. So so it's like a uniform distribution of the input sequence. So and then if we can calculate the running time over that, then we get the expected running time over all inputs of size n. Okay, so the best case is a bogus analysis. Best case for insertion, I said that the case where there is nothing less than the this sorted array. So, but the best case you can just run on a very nice, well designed input and say, oh, my algorithm is doing very nice, So, but that's actually a very bogus logic, because if you give some other input, your algorithm may crash or fail. So best case we do not really do, unless there is some kind of benchmarking we need to do, that okay, see that this is the benchmarking, based on that we do everything. but the worst case is the one usually we do. But as I said, the worst case for insertions is order of n square. Doesn't really matter when the n becomes significantly large. Okay, so all the individual constants which are machine dependent or other lower order terms, they do not really add anything to the final time taken if n is very very large. Okay, so we decided to go for the asymptotic analysis, which is a bigger idea, which gives you a concept of comparing algorithms not based on some real calculation but based on the rate of growth, considering n is significantly large. Please understand, n is significantly large is the very important keyword here. So what it means that if n is very very large, it does not really matter you do individual step-by-step counting or not, but finally what will happen is the highest growth rate function among your component functions will be determining the total running time. So example is here, you see, it's like this is a function I have shown for insertions, or we are getting for best case a linear time, for worst case is a quadratic time. Similarly here you see 3n cube plus 90n square plus 5n minus 6046. These things like 3 or 90 or 5 or 6046, these are called machine dependent constant. If you are using a in a MacBook, probably there will be some kind of constant. If you are using in a Windows laptop, there will be some kind of constant. If you are using in a workstation or a supercomputer, probably the constants will be much lower, much favorable to you. But finally, at the end of the day, which will matter is the highest growth rate function, which is here n cube. I mean, we say that as n tends to infinity, a theta n square algorithm will always eventually beat a theta n cube algorithm. That means if we see that, suppose a linear growth is a theta n function, and then suppose there's a theta n square function. Suppose initially it was not very good, but eventually it will actually, suppose theta n square, suppose this theta n square algorithm, the n square algorithm was initially gaining. Okay, suppose this is the tn and this is the n, initially gaining. I mean, it was having, suppose some particular input n0, suppose this is 500, just assume for 500 we see, wow, my theta n square algorithm is so good. But finally you will see for a certain value of n, the theta n square algorithm will eventually will be eventually beaten by a theta n algorithm. Okay, because that's a linear time algorithm. That's the concept I'm trying to drive in. So here that is called asymptotic analysis. What we do, we ignore machine dependent constants. Okay, we forget this. We forget this 5, 90, 3, everything we forget. We forget lower order terms also. Look at the growth rate of running time. Okay, so these things also we forget. This we forget. So everything we forget. The growth rate. So this will be theta of n cube. This is the highest growth rate function. So that's why it said, look at the growth rate of the running time, Tn, as n tends to infinity, as n becomes sufficiently large, very large, which one is the dominant factor? So that's the running time, okay? Theta n cube. So I will define the concept of theta in a more formal way. But before that, you need to understand theta n cube will give you an upper bound. So whatever be the value of constant, this running time can never be more than n cube, of the order of n cube. That's why we say n tends to infinity. If there is a like this is upper, if you consider upper bound for this algorithm, n to the power 4 is also upper bound, you can see. So it will never ever become more than n to the power 4. N to the power 5 is also an upper bound, but n cube is called a tight bound. Okay, tight bound. It is, if it's very within few constants. Suppose this is 3n cube. If I say theta of n cube, this means this is like within 5n cube. So this is like bounded within 2n cube and 5n cube. Okay, so this is called a tight bound. But this is also bound by like 10 n to the power 5, okay, and greater than maybe 2n, right? So this is also true. So these things are called loose upper bounds, okay? So for this we have small o. For even closer bounds, tighter bounds, we have big O. For small, lower bound, we have small omega. And closer, tighter lower bound, we have big omega. So these are the concepts, okay? So and then very close, very tight bounds are called theta bounds, okay? So when we have both upper and lower bound, please understand very clearly. I'm telling you one more time. 3n cube, suppose our function is 3n cube here. 3n cube is less than 5n cube, greater than 2n cube. See, it only matters what are the constants here. N cube is n cube, both the functions. So this is a very tight, it's a sandwiched bound, okay, upper and lower. So this is called a theta bound, okay. Even if we have, like, let me show you, this is a small o bound. So I will show you one big O bound, suppose like this. Closer, suppose this is like 10 n to the power 4 or n cube. This is a tight bound. If I say 10 n to the power 4, this is a more loose bound, but still it's a big O. But if it's a small o, we can, or this is also a small o, because n to the power 4 is much higher than n cube. So, but if we say it's like 5 n to the power 7, this is definitely a small o. It's a much higher bound. Definitely this running time is less than that, but it's very loosely, it's not a tight. We need a tighter bound to get a best idea. Okay, so like I can give you an example. So you ask me, okay, I need to go to Hawaii for a trip. So what do you think will be the upper bound cost? I tell you, that I went there like 2 years ago. I spent per person like $700. You get a very fair idea. But if I tell you, oh, you can do it by per person less than $7,000. That's also correct. Okay, 700 is less than 7,000, but it's a very loose bound. You do not really get a very close, tight idea. Okay, I should definitely have like $700 per person. Okay, 7,000, 10,000, these are loose bound. These are like small O bound. But if I say, okay, it has to be, within $1,000, this is like a big O bound. Okay, so I will define them more formally. It's a very fun concept. It's a very beautiful concept which tried to show you that forget everything. I don't need to do any calculation with any of the lower order terms or leading constants. What I care, only the highest growth rate. You see, it's a beautiful concept. And this is very important. A higher growth rate function like theta n square can beat a theta n within a short range, but after a certain value of n, it will be beaten by a lower growth function eventually as n becomes larger. Okay, I hope you are getting the concept, and I will now define the the concept of theta, big O, small omega, big omega. Okay, so the small omega, big omega concept is like, if I say the same example I said about Hawaii, if I say it's like $700, that's like theta. If I say it's $1,000, it's like big O. If I say it's less than $10,000, it's small O. If I say it's more than 500, so that is like big omega. And if I say, oh, it's definitely more than 0, you have to spend some money, that's like small omega. Okay, so very loose bound. Can be tight, can be a little bit loose, very tight bound. This is upper bound, can be tight, can be a little bit loose. This is very loose bound. So from here is loose to tight to loose from left to right. Okay, thank you.